Hello my beautiful students, how you people are doing? I guess your preparation is at the peak because your FA2 examination or midterm examination is knocking the door. So at this peak moment, I am here to reveal some secret. What type of secret? So actually I am going to share some most important or relevant questions that you are going to expect in your midterm examination. So you can say that yes, it's a paper leak. Secret, keep it as a secret. So here if you do this type of these chapters and these questions thoroughly, and as you know that we don't only solve the question, we go through the concepts. Your concepts will be clear and your questions will be solved and you are going to get 90 to 95% common out of it. It's my assurance to you. So without further delay, let's proceed with today's topic. So as you can see, first we will start with the chapter Aldehyde, Ketones and Carboxylic acid. Then we will proceed with chemical kinetics, amines and biomolecules. So slowly, let's start with the first chapter. So you can see first little bit number distribution I have given here. So very small answer type question you can expect to. Among this MCQ will be included, and later on you can expect long answer type question out of this particular chapter. Okay, so see, it's an organic chapter. So I know you people sometimes feel that organic chemistry is very hectic because so many name reactions, so many conversions type of thing you are going to expect, right? But trust me, if you find out the keywords out of the questions and you try to solve the question one by one, part by part, not at a whole, right? You will get the answer in a proper way. So let's proceed with the first question. You can see, so among the following alkyl benzene, which one will not give the benzoic acid on oxidation with acidic KMnO4 solution? Okay, so here as I told you, find out the keywords. First keyword is alkyl benzene, right? Second one is will not give, right? Next is benzoic acid, and the last one is acidic KMnO4. Now analyze one by one, right? See, I am having acidic KMnO4. By looking at the question, you can understand it's a reagent. So now imagine what is the role of this reagent, right? What is the role? So whenever you will see this type of reagent, they work as a very strong oxidizing agent. Very strong oxidizing agent, right? So now let me just tell you something. This particular strong oxidizing agent will convert the entire alkyl group to the carboxylic acid when that benzylic carbon will be having hydrogen. What is benzylic carbon? Benzene with a carbon, then some other group, whatever it is there, it can be, but this first carbon is called benzylic carbon. This is called benzylic carbon, right? This benzylic carbon must have hydrogen. This benzylic carbon must have hydrogen. This is the key concept to solve this question. So once this benzylic carbon is containing hydrogen, then you can say they can convert the entire group to benzoic acid. If it is not, then it will not be able to convert, right? So first case you can see it's a toluene, right? So definitely toluene, this is a benzylic carbon, this is the benzylic carbon, right? And it is having 3 hydrogen. So definitely it will be converted to benzoic acid whenever the strong oxidizing agent will be used. Now look at this one. If you just look at this one here, for this case, I am having 1 hydrogen. I am having at least 1 hydrogen, right? So okay, for the better visibility, let me just use the red one. So here actually in this is my benzoylic carbon, and this benzylic carbon is having at least 1 hydrogen. So this also can be converted to benzoic acid as well. Now just look at this one. This is ethyl benzene. This is also having the benzylic carbon, and it is also having 2 hydrogen, right? So it also can be converted to benzoic acid. But now if you just look at this one, this particular carbon, this is a benzylic carbon, this has no hydrogen. Hence, this cannot be converted to benzoic acid if you give KMnO4. Okay, if you give that acidic KMnO4 solution. So, what is the key concept? There should not be any hydrogen at benzylic position. I guess you understood this concept, so option B is going to be the correct one. So again I am telling you, don't by heart the concept, rather focus on the concepts. Don't by heart the answers. Okay, remember these things. Okay, so let's proceed for the next one. Here comes again a big question. So whenever students used to see this big question, they avoid it. But please take your time, find out the keywords. Okay, and the answers sometimes it's hidden in the question itself. Okay, let's go through. An organic compound with the molecular formula C9H10O forms 2,4-DNP derivative, reduces Tollens reagent and undergoes Cannizzaro reaction. So they gave the keyword here. You can see it forms 2,4-DNP derivative, means it gives positive result in 2,4-DNP test, right? It reduces Tollens reagent, means it's something that can reduce the Tollens reagent. Okay, Tollens positive, Tollens result positive, and it undergoes Cannizzaro reaction. Okay, now you can see on vigorous oxidation it gives 1,2-benzene dicarboxylic acid. So now you have to find out the compound. So I am having 2,4-DNP positive. I am having 2,4-DNP positive. I am having Tollens positive. It means what? It means what? When you can get both of them positive, definitely my compound must contain some aldehyde group. So definitely I am having some aldehydic unit, right? So now you can see it gives some positive result with the Cannizzaro. Means Cannizzaro reaction, when it takes place, if you can recall, if there is no alpha hydrogen present in my compound. So definitely by looking at the product, means benzene dicarboxylic acid, means benzene ring by default is there. So if I just start drawing the structure, benzene ring must be there. Along with that, one aldehyde group should be there, and that aldehyde group, that aldehyde carbonyl carbon, should not have any kind of enolizable hydrogen or alpha hydrogen. So it is only possible if the aldehydic group is attached directly to the benzene ring. See, this is the alpha carbon, right? This is the alpha carbon and there is no hydrogen at all. So this is a perfect condition to give you the Cannizzaro. I guess you understood. By looking at the answer, you can simply judge my compound is having a benzene ring. And then about the functionality, look at the tests. Tollens positive, 2,4-DNP positive. It means definitely aldehyde group is there. Now, what type of aldehyde? What type of aldehydes are there? The way it should not have any kind of enolizable hydrogen. It should not have any alpha hydrogen, right? Then only it can proceed with the Cannizzaro test, right? So, there is only one option. Like this. Now just look at the options. Now look at the option which thing can give you on vigorous oxidation can give you 1,2 benzene dicarboxylic acid. Okay, so vigorous oxidation means you are doing like a very random oxidation, random in the sense very strong oxidizing agent you have applied over here, and this entire aldehydic group will be converted to COOH. And in another position, you can just look at that. This is your one position definitely. And in another position, so simply I am adding it in the two position, CH2, CH3. So definitely on being oxidized, it will give you surely the carboxylic acid for the aldehyde, and the entire ethylic group will be oxidized to give you the carboxylic acid. So you don't need to proceed with the further option, you already got the answer. Again, just for a recapitulation, who understood it's better? While you are noting down, just listen what I'm saying. Find out the keywords, okay, and then try to connect the puzzle. How? First you can see 2,4-DNP test and tolerance reagent, tolerance test, whatever you want to say, they are giving positive result, okay. Next, it undergoes Cannizzaro reaction. So tolerance and 2,4-DNP both gives positive result in case of aldehyde, right? And Cannizzaro also is possible in those aldehydes which don't have any kind of alpha hydrogen. So, and now looking at the product like 1,2-benzene dicarboxylic acid, so there must be a benzene ring. So benzene ring you draw, then attach one aldehyde, so CHO. Attach one aldehyde so that it should not have any kind of enolizable hydrogen or alpha hydrogen, so that it can proceed for the Cannizzaro reaction. Got it? Now look at the options, right? As you can see, 1,2-benzene dicarboxylic acid they are asking, 1,2 position. So definitely in the 1 position it will be converted to carboxylic acid, and the 2 position the ethyl group should be there, right? That will be completely oxidized to give you the carboxylic acid. I guess you understood this. Let's proceed for the next one. Here you can see which of the following compound is most reactive towards nucleophilic addition reaction. So whenever you're just thinking about the nucleophilic addition reaction, just breaking down the term nucleophile. Nucleophile means it loves something positive, right? It loves a center that must be positive. So whenever you are just going to do the nucleophilic attack, then you keep it in your mind that your attacking center must be positive, little bit electropositive in nature, right? So to determine all those things, if the attacking center, that particular center where the nucleophile will attack, if it will be positive or negative, or it will be electronically enriched, you must study electronic effect. Electronic effect in the sense, you know, plus I, minus I, and then plus R, minus R, plus M, minus M, this type of effect you know very well, electronic effect. Next you have to study steric hindrance. Why steric hindrance? Why steric hindrance? Because let's say I am having my attacking center very feasible for the nucleophilic attack. Fine, it's a very electropositive in nature, partial positive charge is there, nucleophile wants to attack on it. But surrounding to it, there are some bulky groups. So nucleophile will not get space to attack over there. So ensure that the particular center, the particular electrophilic center is open enough. It's open enough to the nucleophile. So that's why second factor is steric hindrance. Okay. Now if you just judge on these two factors, let's decide what factor, in which case it's predominating. Okay, so look at the first case. For the first case, CH3 group is there, so CH3 group is having plus I effect, right? CH3 group is having plus I effect, and here I am having carbonyl carbon. Fine. Here I am having, you can see, benzene ring. Okay, so benzene ring, you can see benzene ring actually what it does, it gives electron, it supplies electron, right? Okay, now here if you just look at that CH3, both the side you are having plus I, and here you can see one side you are having plus I, another side you are having resonance stability, right? Resonance effect, right? So now you can see the center, the attacking center is the carbonyl carbon. For every cases, attacking center is the carbonyl carbon. So just see now just look at that, in which case the carbonyl carbon is most electropositive. So here if you just look at this particular case, you're looking this, let's start from here. If you just look this particular case, both CH3 and benzene ring is supplying the electron towards this carbon. towards this carbonyl carbon, right? From the benzene ring as well and from the CH3 as well. This carbonyl is getting supplied electron, right? Now look at this. From one end benzene is supplying electron to this particular carbonyl. Another end it is hydrogen only. Fine. So electropositivity decreases here and then here as well, right? But I need electropositive. Now just look at these two options. Now just look at these two options. So if you just look at this is an aldehyde, this is an ketone, right? So if you just normally deal, aldehyde is more reactive than that of ketone. It is just because of the steric effect. Okay. If any nucleophile wants to attack on this carbonyl carbon, here you are having two methyl group, right? 2 methyl group is bulkier than that of single methyl group. So nucleophile can attack here more easily than that of this, right? And here also you can see here also 2 plus I, here also 1 plus I effect, but here steric effect is going to be the proper answer because aldehyde is more reactive than that of ketone because of the steric factor. Okay, I guess you understood. So the answer is going to be A. Let's proceed for the next one. Okay, so the correct order of increasing acidic strength. So let's see what are the compounds they have given. So they have given ethanol, right? Okay, phenol. Let's start from phenol. They have given phenol. Okay, anything else? Ethanol, CH3, CH2, OH. They have given chloroacetic acid. Cl, CH2, COOH. Another option they have given acetic acid. Okay, just by looking at the question you can understand that these two are acidic, right? The name itself is acid and these are the alcohols. Okay, so definitely these two will be at the last. Okay, anyway, there are other options to explain this as well. So whenever any acid after releasing its acidic hydrogen, it is called as conjugate base. It is called as conjugate base. Okay, so now just let me just give you a real life example just to connect the thing. Like let's say I have to go outside for some work. Okay, I have to leave my family for some work purpose. But if I see that after my departure, my family will be in uncertainty. There will be some disruption. So I will my departure will not be that easy, right? But if I can see that after my departure my family will be happy, it will be all right, they can manage everything, so my departure will be easier, right? So for the acid as well it is the same case. Okay, if hydrogen while leaving it feels after my departure, after my release, the system that is called conjugate base, it will be stable. Then the H plus will be released nicely. It will be nicely acidic, right? But if it feels that if I leave, then my system will not be that much stable. It is not having some stability factor. Then releasing of H plus will be way too difficult, right? So what you have to ensure? You have to ensure the stability of the conjugate base. If the conjugate base is stable, then you can say yes, acidity is very high. I guess you can understand. So now let's see this same parameter if it is applicable here or not. So first, if you just look at that, let me just take out this example at first. Sorry. Let me just take out the example ethanol. So ethanol, if this acidic hydrogen it releases, my system will be something like this: CH3, CH2, O minus, ethoxide, right? So now if I draw the conjugate base for this, mean phenol, it will be phenoxide. Okay, so if I compare them, this phenoxide ion is having stability because of the benzene ring. This negative charge gets delocalized. Always remember, when there is a charge delocalization possibility, when there is a possibility of the dispersion of the charge, means, see, let me just give you a very simple example. I am holding 3 bricks together, right? I have to put some more effort, right? But 3 of us, 3 more people, with 1 brick, each of us. This is called dispersion. So the weight is distributed. Similar thing happens in this case as well. If you can disperse the negative charge, if you can delocalize the charge, that is a resonance, then the system gets some extra stability. It is not possible here. It's not possible here. So definitely this is more stable than that of this, and hence phenol is more acidic than that of ethanol. Now let's compare these two. First one is your this one. Let's take this one, CH3COOH. So if you just draw the structure, it's like that, right? And another one I am having chloroacetic acid. It is something like this. Okay, so here CH3 group, if you just look at that, if you are having CH3 group, it is having plus I effect, means already oxygen is having negative charge. Again, because of CH3, the electron density on oxygen will be increased. So if oxygen is so negative, why it will release hydrogen? Hydrogen is electropositive, right? So definitely from here you can say that this particular thing is more acidic than this. Why? Because chlorine group possesses minus I effect. Minus I effect means it pulls the electron cloud density. It takes away the electron cloud density from the oxygen, and oxygen becomes less electronegative, and hence charge dispersion also takes place, and oxygen can release the hydrogen nicely. So I can write the order, I can write the order like this. Okay, now you can ask this question like why phenoxide and acetic acid, whenever I am comparing, then why I am putting acetic acid at the front, right? So if you just look at the phenol, I understand it is having some very good resonating structures, canonical forms, okay, and here also I am having only 2 canonical forms, right? So if I draw the canonical forms, it will be something like this. So I'll be having the form something like CH3, CO minus, and here I am having, I'll be getting double bond O, right? So this type of 2 canonical forms I will get. But if you just imagine, if I draw at least 1 canonical form of the phenoxide, you can see that it will be something like that. Further I can proceed like this, it will come like that. So this type of canonical form I will get. But here you can see oxygen is holding the negative charge. Oxygen likes negative. It is holding the negative charge. It's a good thing. But here the case is something, if a patient is diabetic and you are giving the sweet, right? Here carbon is electropositive in nature, but you are giving a negative charge here on the carbon. By default it will come. If you proceed with the resonance, by default it will come, right? So the better option is oxygen is holding the negative charge because it is more electronegative. So that's why these canonical forms of the acetate anion is more stable than that of the phenoxide. I guess you understood. Now the concept is clear and you got the answer as well. So if you just look at the answers, ethanol will come first, then phenol, then acetic acid, then chloroacetic acid. I guess the option is C. So I guess you understood this. Let's proceed further. the compound can be prepared by the reaction of what? Anyway, so whenever you can see it's an S star functionality. Okay, it's an S star functionality. So whenever you will see this type of S star, so definitely please be assured that two compound gets condensed, maybe water, maybe some hydrohalogen type of compound gets released, and you will get the S star type of compound. So if you just simply look at the answer phenol and benzoic acid, it's not possible for the like in presence of NaOH, it's not possible for the condensation. Here if you just look at the second option, phenol and benzyl chloride. Okay, so if you this will give you this compound, you can see I am showing you, this is my phenol and I am having benzyl chloride. Benzyl chloride is something like this. Right? So here COCl, this is C, okay? This is COCl. So here what happens whenever you are giving pyridine, so this hydrogen and this halogen will be eliminated in the form of HCl, okay, and you will get the desired compound. Okay, I guess you understood this. Let's proceed for the next one. Okay, so the reagent which does not react with both acetone and benzaldehyde. So you have to find out a compound. It should not react with both sodium, with both acetone and benzaldehyde, right? So for this particular case, just look at the options. First option is sodium hydrogen sulfide. So in the last video also I told you this particular compound is very much important for the purification of aldehyde, okay, because it reacts both with aldehydes and ketone, but the adduct that it forms with aldehyde, that is water soluble, right? So definitely by default I am telling that this sodium hydrogen sulfide, it works as a nucleophile and hence it works both with aldehyde and ketone. Okay, now you can see phenylhydrazine. So here you can see phenylhydrazine. Now here you can see, if you just look at the phenylhydrazine, that is also it's reactive towards both acetone, aldehyde and ketone. Next option you can see Felling's solution. So but Felling's solution here, it is a mild oxidizing agent. We know Felling's is a very mild oxidizing agent. Okay, so here for this case it will react with the aldehyde, but it will not react with the ketone group. Okay, so you already got your answer. Now here you can see Grignard reagent. If you just look at that, Grignard reagent is also a very strong one that also react with both aldehyde and ketone. Okay, so your option is going to be the Felling's solution. Let's proceed further. Okay, so here you can see Cannizzaro's reaction is not given by, and you are having the option. So this thing also I told you. Okay, the last thing is one of the board alert question. Please be assured. Okay, for this case also it is one of the board alert question. Board alert zone you can say. Okay. Last video also I explained a little bit about it. To perform the Cannizzaro reaction, you must have enolizable hydrogen. Enolizable hydrogen indicates alpha hydrogen, right? So let's check where I am having alpha hydrogen and where not. So for the first case, this is my aldehydic carbon, this is my aldehydic carbon, and this is my alpha hydrogen. This is my alpha hydrogen. Okay, as you can see, alpha hydrogen is not having any hydrogen, so definitely it will give you the Cannizzaro. Okay, this is benzaldehyde, this is my aldehydic carbon, and this is my alpha. So alpha carbon is not having any hydrogen, so definitely it will also give me the Cannizzaro test. Look at this one, it is only having one carbon, there is no alpha carbon at all, right? So there is also no alpha hydrogen, and hence it also give the Cannizzaro. But look at this, this is your aldehydic carbon and this is your alpha carbon, and it is having 3 alpha hydrogen, right? So once it is having the 3 alpha hydrogen, so definitely it will not proceed for the Cannizzaro reaction. Always remember a very important key factor, that is Cannizzaro reaction, they don't require any kind of alpha hydrogen, whereas aldol condensation reaction, aldol reaction, you must have known the name, aldol reaction, they need the alpha hydrogen. Okay, always remember this. Cannizzaro, they don't require, aldol reaction, they require it. Okay, let's proceed further. Okay, so this type of conversion reactions are quite easier because they will not give you that much hectic or that much difficult type of thing. Direct reagent, direct answer. Okay, first you can see this particular reagent, that is 40% H2SO4 and HgSO4. This is the reagent for the oxymercuration demercuration. This is also a board alert zone. Okay, this is also a board alert zone. This is OMDM type of reaction, oxymercuration and demercuration. Okay, and here the OH group gets added, OH group. Okay, and the addition is a kind of Markovnikov addition. Okay, so Markovnikov addition, if you can recall, Markovnikov addition is that addendum, means whatever is going to be attached, that will be attached where there are less number of hydrogen, right, where there are less number of hydrogen. So you are having, this is this one alkyne group, alkyne unit. So alkyne containing 2 carbons I am having, this one and this one. So now where I am having less number of hydrogen, definitely in the middle one, right, there is no hydrogen at all, right? So OH will be added in the middle carbon. Okay, so if I just write the reaction normally, CH3 C triple bond CH, and I am not writing the reagent, you can see I am just simply writing OMDM, means oxymercuration demercuration, and as a result of this you will get C. Here I am having OH, here I am having double bond, and here I am having CH2. Hydrogen will be added here. This is the Markovnikov addition. First step is Markovnikov addition. Okay, always remember here also one thing I always prioritize, I always keep telling the students, remember it in this way, whenever you are doing OMDM, oxymercuration demercuration, the OH will be added in the intermediate carbon, middle carbon. Okay, but if you are doing hydroboration oxidation, HBO, with the BH3 and THF, right, the OH will be added at the terminal carbon. Okay, always remember this particular rule. Okay, OMDM, whenever you are doing, OH will be added in the middle carbon. Whenever you are doing hydroboration oxidation, that is also OH addition, OH will be added in the terminal carbon. Okay, so let's proceed further. Isomerism. So to understand further what it will give you, I mean like it will, they gave already, it's acetone. Okay, how they are giving it, you can see you are having one in unit and one all unit, means enol, right, it's an enol. So whenever I am giving you the term enol, please be assured that they are performing ketoenol tautomerism. Yes, they are performing ketoenol tautomerism, and hence you are getting one ketone group. So I have to give one equilibrium sign here, like this. Okay, so now let's proceed the question what they are asking. Structure of A and type of isomerism in the above reaction. So definitely structure of A you got. So what's going to be the answer for this case? So let's normally nomenclate it. So normally if you just number it 1, 2, 3. So here I am having prop 1 in 2 all, right? Prop 1 in 2 all, and it is showing tautomerism, because it is an enol and it's showing tautomerism reaction. Okay, so let's find the option. Let's find the option. This one, right? Option D is the correct one. Prop 1 in 2 all, and it will show tautomerism. So this is my enol form and this is the keto version of it. Okay, I guess you understood this. Let's proceed for the next one. Again a conversion type of reaction, I mean a question. Let's proceed further. Here you can see CH3CHO. Let's do the reaction at first normally. So CH3CHO, you are having one aldehyde group, okay, and you are giving Grignard reagent CH3MgBr, fine. Then you have to proceed with H2SO4. So if I just do this type of reaction, I guess you people know, you will get one OH group, right? One OH group attached to the carbonyl, right? So finally, if you treat it with this, first this, and number 2 H2O. So I guess you know this CH3 minus will be attacking here, this will go there, so OMgBr will come. Let me just do a little bit step for you. So CH3C, here O minus will takes up the MgBr unit. It will take the MgBr unit, and here the CH3 will be attached, and here by default one hydrogen was there. Further, if you are giving water, so once you are giving water, entire this will go and you will end up with something like this, CH3C. Here you are having OH, here I am just writing this CH through here like that. This is something that you will get, right? So this is my A. Okay, next what I have to do is H2SO4. H2SO4, and I am giving heat to the system. So always remember, whenever you are giving H2SO4 and you are heating the system, it will undergo dehydration. So as you can see, I am giving some strong acid. It is acid catalyzed dehydration reaction. So from my system, one hydrogen and one water will be released. So one hydrogen, one water, if it released, then it will form a double bond. So you will end up with this type of thing. Okay, so now what is the next step? Now hydroboration oxidation. So here hydroboration oxidation, I guess you can remember the reagent a little bit, BS3 in THF medium, and later we give some peroxide or peroxy acid. Okay, peroxy acid. So if you proceed with this, just now I told you while doing the last concept that whenever HBO you are going to proceed, the OH will be attached but at the terminal carbon. So definitely it will be something like this, right? So this is going to be your C. This is your B. Let's go through the question now. Now compound A and C in the following reaction. So this is my compound A and this is my compound C. Okay, so if they are identical, positional isomerism, functional isomerism, or optical isomerism. So there is no chance of being optical isomers. Identical to definitely it's not, because the position of OH varies. So that's why directly you can tell they are position isomers. Because everything is similar, the molecular formula is similar, functional group is also similar, that is used. Optical isomer, no, because there is no chiral carbon. Hence, you can say it is a positional isomerism. Okay, because the position of OH group only differs. I guess you understood this. Let's proceed further. Okay, so here I am having which is the most suitable reagent for the following conversion. So here what I am having, let's proceed with the next one. Which of the following compounds will give butanone on oxidation with alkaline KMnO4? So here also there are different keywords that are given that will help you to solve the answers. First is KMNO4, alkaline KMNO4. It's a very strong oxidizing agent. And you can see butanone. Butanone means it's a ketone, right? So this particular thing, this strong oxidizing agent KMNO4, last few questions ago also I told you it will oxidize the secondary alcohol, right? It will oxidize the secondary alcohol. Now let's check where I am having the secondary alcohol. So butan 1-ol. So I am having this one. This is butan 1-ol. You can see it is 1 degree, and I am having butan 2-ol, CH3, CH. Here I am having OH, CH2, CH3. This is my 2 degree alcohol, right? This is 1 degree alcohol, this is 2 degree alcohol. So this will be oxidized nicely to give you the butanone. So once you are giving KMNO4 here, you will get one ketone group here. Right? So this is going to be the correct answer. Let's proceed further. It's a direct question. Clemenson reduction is one of the most important question for the board examination and for the midterm as well. So you can see in Clemenson reduction, carbonyl compound is treated with, and the reagent you have to find out. So definitely it's a zinc amalgam in HCl, no other acid, only HCl. Okay, so this is going to be the correct answer. It's a direct question. Let's proceed further. Here you can see as the size of the aldehyde molecule increases, the odor becomes first more pungent, more fragrant, less fragrant, no change in the odor. So definitely whenever there will be a size increased for the aldehydic, compound, so there will be a change in odor, and let me tell you, it will be more fragrant. Higher order aldehydes, they are used for the making of perfumes, right? So definitely it will be more fragrant. Okay, let's proceed. Here you can see the reagent useful for the separation and purification of aldehydes. So earlier also I discussed these things with you. This is one of the most important zone actually to ask the question about it. So here you can see I told you, if you are having the mixture of aldehyde and ketone both, you have to add sodium hydrogen sulfide. So sodium hydrogen sulfide, it works as a nucleophile. It forms adduct with both aldehyde and ketone, right? And that aldehydic adduct, the adduct it will form with the aldehyde, it is water soluble. Okay, so we will purify it and we will further give some dilute HCl or NaOH, we will get back our aldehyde, okay, from the adduct. Okay, so definitely sodium hydrogen sulfide is going to be the correct answer. Let's proceed. This is also a direct question. It's directly coming from the name reactions, right? So see, first one is Gattermann-Koch reaction. So Gattermann-Koch reaction is what? It is something like from the benzene you are converting benzaldehyde. This is your Gattermann-Koch, right? So for this case, I need the reagent carbon monoxide. So for A, I am having option 3. Next is Stefan's reagent, right? So basically in Stefan's reaction, what basically happens? I am having, let's say, cyanobenzene, benzene with one cyanide unit. Okay, it will be converted to benzaldehyde. Okay, so for this particular case, I need the reagent stannum chloride. Okay, you can see stannous chloride in the presence of HCl. Okay, next you are having Rosenmund reaction. What is Rosenmund reaction? Rosenmund reaction is you are having benzoyl chloride, that is benzene with COCl. okay, and this will be reduced to give you benzaldehyde, right? This will be completely reduced to give you benzaldehyde. Okay, for this particular case I need the reagent 4, okay, H2 in palladium BaSO4, right? Next is Etard reaction. Okay, in Etard reaction what happens? Basically I start with toluene, okay, and I end up with benzaldehyde. Okay, this particular thing is basically chromium chloride, CrO2Cl2. Okay, so now if you just look at the options, A is 3, B is 1, C is 4, D is 2. I guess the option is B. The correct option is B. So I guess you understood this. So let's proceed further. Here comes the long answer type question that will contain the 5 marks. Okay, so here also you are having 2 parts. So for the each part marking will be there. So let's proceed for the first question. Between methanol and ethanol, which would undergo aldol condensation, and write the chemical reaction involved in it. Okay, so you are having methanol. Methanol is this one. This is formaldehyde, right? And you are having ethanol. Right? So one primary condition that I already told you, for performing aldol reaction, aldol condensation reaction, you must have alpha hydrogen. So what is the primary condition? Must have alpha hydrogen. For this case, no alpha hydrogen. For this case, yes, alpha hydrogens are there. 3 alpha hydrogens you are having over here, right? So this will perform aldol condensation reaction. Now let's proceed how they will perform for the aldol condensation reaction. So if you are having another unit of this, let me just arrange them in such a way so that you understand. CH2, C double bond O, hydrogen. So now once you are giving dilute base, dilute NaOH, let's say, it will form this thing, CH3, C, here you are having OH, CH, let's write the hydrogen here, and you are having one aldehyde, right? Now if 1 unit of water is released, you will get that famous alpha beta unsaturated unit, alpha beta unsaturation. That is one of the key functionality that will tell you that yes, this particular compound came from the aldol condensation reaction. Okay, so you will get something like CH3, CH double bond, CH, CHO. So this is, you can see, this is the carbon, this is the aldehyde carbon, here this is alpha, this is beta. In the alpha and beta position you are having the unsaturation, right? So you can see alpha beta unsaturated compound, and this particular compound is named as crotonaldehyde. Okay, I guess you understood the first part. Let's proceed with the next one. Okay, although phenoxide ion has a greater number of resonating structure than that of the carboxylate ion, carboxylic acid is a stronger acid than that of the phenol. So this particular thing we already covered in the MCQ zone, but still for your convenience, let me just discuss once again. See, once you are proceeding with the phenoxide, you are having this type of ion, O minus, this will jump here, this will open up. As a result of this, you will get something like this. Right? It will be continued, right? so many resonating structure, 2 to 3 resonating structure you will get out of it, right? And here if you just draw the resonating structure for the what acid they gave? Carboxylic acid. Any kind of carboxylic acid we can take, normal acetic acid we can take. So here if you just do the resonance, you will get two equivalent resonating structure. Here you are having non-equivalent resonating structure, and here you are having two equivalent resonating structure, okay, where oxygen is holding the negative charge. But here you can see non-equivalent structure. Why I am telling? Because here carbon is holding the negative charge. Carbon being electropositive, it doesn't like the negative charge at all. So that's why it always likes positivity. So whenever you are giving negative charge on it, by default the entire thing becomes unstable, okay. So just look at this. This is the answer. Just overall I just wrote it. You can just go through once. You can pause your screen and you can go through once. You will understand, I guess. So let's proceed further. I guess you understood. Here you can see next question. Give the chemical equation for the conversion of propanenitriles into corresponding ketones by using phenyl magnesium bromide, and write the IUPAC name of the product, okay. So let's at first write the compound. So propanenitriles is going to be something like this: CH3 CH2 CN, right? So once I'm giving the, what I'm giving here, phenyl magnesium bromide, sorry, C6H5, and I'm having MgBr. So what will happen? You know it very well. Let me just break down the structure. Okay, so C6H5, this is negative part, delta negative, this is the delta positive part. So this is the nucleophile, it will attack here and this bond will open, right? So as a result of this, you will get something like CH3, CH2, and here along with this carbon, the C6H5 unit will be attached, and here with the nitrogen you will be having MgBr, right? Okay, so now what you have to do? Give some water, this entire thing will be gone, and as a result of this, you will end up with something like this: CH3, CH2, C, here you are having double bond O, and here you are having C6H5. Okay, means one benzene ring, right? So now let's nomenclate the system. So 1, 2, 3. In the one position I am having phenyl. So one phenyl, and I am having 3 carbon system, hence propan. In the one position I am having ketone, hence one. Okay, I guess you understood this thing. Let's proceed with the next part, that is HVZ reaction. Hell-Wohlert-Zelensky. So here it's a very easy reaction actually. You must have one carboxylic acid with alpha carbon. Okay, always remember the key functionality. Okay, carboxylic group with one alpha carbon. Okay, now any halogen if you want to attach, let's say you want to attach bromine, that bromine will be attached in the alpha carbon. Okay, so let's say you are having R CH2, because I need one alpha carbon, COOH. This is my alpha carbon, right? Here I am giving the reagent is Br2 in phosphorus, right? And second reagent I have to give some water. So what will happen? In the alpha position itself the bromine will be attached. So R CH Br COOH. This is the reaction. Okay, this is a direct question actually. I guess you understood these things very well. So let's proceed for the next one. So let's proceed for the next question. So here the question comes, write the mechanism for the addition of HCN to carbonyl compound in the presence of base. And the second part is, aromatic carboxylic acid does not undergo Friedel-Crafts reaction, give reasons. Okay, so one by one we will proceed with the question. So first is, whenever HCN is given, in base, it actually forms CN minus, where carbon is having one extra pair of electrons. Now along with that you are having water, fine. Now you are having carbonyl group. So here in this carbonyl group, this carbon is the electrophilic center. So Cn minus, the extra pair of electron will attack here and the double bond O will be opening up, and this will give you one tetrahedral type of intermediate. So this particular thing is a tetrahedral intermediate that you will get. Further, after releasing, whenever one H plus is added into the system, then you will get back this type of compound, and the name of the compound is cyanohydrin. Okay, so as you can see, once you are just giving HCN in any kind of carbonyl compound, it will give you the cyanohydrin type of compound. So in a single carbon, OH and CN attached. Okay, so I guess you understood this. Let's proceed with the next part, that is the aromatic carboxylic acid doesn't undergo Friedel-Crafts reaction. What is the reason? So first of all, the carboxylic acid, this particular group, you know very well, it's an electron withdrawing group, right? It's an electron withdrawing group, right? So being electron withdrawing group, it deactivates the ring. Hence, you can also call it as ring deactivating group. See, whenever you are doing Friedel-Crafts alkylation or any kind of Friedel-Crafts reaction, it's basically an electrophilic attack, right? So whenever electrophilic attack is going to take place in benzene, benzene must be very much electronically enriched, right? But here carboxylic acid is particular COOH group is taking away the electron cloud density from the benzene. As a result of this, the nucleophilicity of the benzene or electron dense benzene becomes electronically lagging, electronically poor for the further electrophilic attack, right? So as a result of this, Friedel-Crafts alkylation or any kind of Friedel-Crafts reaction, it will be difficult to take place here. Okay, I guess you understood this reason. Another reason, this is reason number one. Another reason is, in Friedel-Crafts reaction we use AlCl3. So what is AlCl3? It is an Lewis acid, right? Here what Lewis acid or AlCl3 does, it makes some complex with the oxygen. Okay, and that bond becomes very much strong. So before it further proceeds for the electrophilic substitution reaction, it makes an adduct with the carboxylic acid oxygen. So further it prevents the Friedel-Crafts reaction. So these two are the reason behind it. I guess you understood this. Let's proceed for the next question. Okay, so here we are going to start the next chapter, that is amines. This is a little bit marking pattern that I have given. Usually from the amines you can expect 2 questions of a very small type, and large answer type you can expect at least 1. Okay, so let's proceed. The first one, decreasing order of the basic nature of the in aqueous solution. So here I guess you know that there are 2 types of order that we see for the primary, secondary and tertiary amine. In normal gaseous form there is a different order, and in aqueous there is a different order. The reason is there are kind of different type of effect in water, hydrogen bonding, solvation effect. Because of this, 2 degree amine becomes like a more stable or more basic in nature. After that it comes 1 degree, then if you want to compare it comes ammonia, then it comes aniline. So this abrupt behavior is just because of the different type of solvation effect or hydrogen effect, this type of intermolecular interaction. Okay, so as you can see, in accordance to that, the option C is the correct one. Okay, so let's proceed for the next one. Here comes identify the product in the following reaction scheme. Okay, so let's do one by one. First I'm starting with aniline. So whenever you are having aniline, let's give Ac2O, and as a result of this you will end up with benzene NHCOCH3. Fine. Next I will proceed with Br2CCl4. Here you will get one para substituted product. So bromine will be substituted in the para position, and if you give water further, this entire thing will be converted to NH2. And here as usual it is the bromine. So this is the entire conversion. So let's name it. It's definitely para bromo aniline, right? So this is going to be the correct answer. Let's proceed for the next one. Okay, so first let's do the reaction. As you can see, this reagent is very much common to all of us, NaNO2 and HCl. From here I guess you know that in situ formation of HNO2 that actually diazotize the compound, right? So diazotization will take place. So if you just want to write the product A, it will be benzene diazonium chloride, right? Further, if you give HbF4, then the entire thing will go and it will be substituted with fluorine. So you will end up with fluorobenzene. So if you just look at the options, option D is going to be the correct one, benzene diazonium chloride, and after that you will end up with the fluorobenzene. Let's proceed for the next one. You can see nitrogen gas is liberated when HCl plus NaNO2 react with the following compounds. So we have to find in which case if HCl and NaNO2 react, N2 gas will come out, right? So one by one we will see. First let's proceed with CH3, CH2, NH2. Right? If you give, I'm not writing the reagent, this reagent you have to add here. If you give this reagent here, you will end up with alcohol, CH3, CH2, OH. Along with that, definitely nitrogen gas you will get, and water you will get, and here NaCl you will get, right? Because sodium is here. So I'm not balancing the reaction, I'm just showing the products only. You can see nitrogen gas will be eliminated here. Okay, next proceed with urea. Urea is CONH2 whole twice, right? So once will you proceed with the reagent, that is HCl and NaNO2. For this particular case also you can expect nitrogen gas, along with that CO2, along with that water and NaCl, right? So here also nitrogen. Now you can proceed next one, that is CH3CONH2, CH3CO NH2. For this case, if you add that reagent HCl and NaNO2, you will end up with acetic acid CH3COOH. Along with that, definitely nitrogen gas plus water plus NaCl. So here also you can see I am having nitrogen gas. Let's proceed. Next one I am having C6H5 CH2 NH2. For this particular case, you will end up with N2 plus Cl minus plus NaCl. So you can see for this case you are not having the nitrogen gas as eliminated. So from 1, 2 and 3 you are getting the nitrogen gas. So C is going to be the correct one. Okay, so let's proceed for the next one. Okay, so as you can see the first step, by looking at the particular thing you can understand it's a part of Sandmeyer's reaction, right? CuCN and KCN. So definitely you are having this type of compound, benzene diazonium chloride. If you give here CuCN and KCN, then definitely entire N2Cl will be converted to Cn, that is cyanobenzene, right? So once you are giving some reducing agent, lithium aluminium hydride, that Cn group will be reduced completely and you will get CH2 NH2, right? Further, if you proceed with HNO2, then you will end up with CH2OH. So this is the thing. So let's look at the option. It's actually, the name of the thing is benzyl alcohol, right? So option C is going to be the correct one. Let's proceed further. Okay, so the product formed from the following reaction sequence. Okay, let's do the reaction. I am having cyanobenzene, right? Okay, so here at first I have to reduce it. So I am giving lithium aluminium hydride. So just in the previous slide we did it. Here it should be CH2 NH2 in the first case. Next what I am giving? I am giving here NaNO2 and HCl. NaNO2 plus HCl. So in situ HNO2 generation will be there and we will end up with the benzyl alcohol, right? And little bit water also in this step it is needed. So we can directly proceed with this, plus nitrogen will be eliminated. Okay, just a minute, one slide earlier I want to go. Okay, for this particular case, once you are giving here also NaNO2 plus HCl, for this case also you can do CH2OH, So let's correct it once. You can proceed with the formation of CH2OH. And here also CH2OH, and here also actually nitrogen is formed, but as you can see the 1, 2, 3, 4 means all the options you can get nitrogen gas as a like byproduct, but here the options are not given. So actual answer, if I just want to write, it is 1, 2, 3 and 4. This is the correct answer. Okay, so yeah, let's proceed for the next one. This thing we already did, I guess. This thing also. Okay, so what is the final product that you can see? It's option B, that is a benzyl alcohol. Okay, so I guess you can see how in from the which zone the repeated questions are coming. Okay, let's proceed for the next one. Okay, so now we are proceeding with the long answer type questions. So first question is, which type of amines answers for the carbylamine reaction, that is the isocyanide test, and explain this reaction with an example. It's a direct question basically, carbylamine test that you have to write directly, and as you can see it is for the primary amine, the test for the primary amine, and you will get some foul smell out of the reaction, right? So you can see here the first answer is your primary amine, that will give you the positive test. And you can see how the reaction takes place. RNH2 you are having, you have to give chloroform in alkaline media, you have to give KOH. Okay, so here alkyl isocyanide, this is of foul smell. Okay, this offensive smell is the identity that you are actually having the primary alcohol, primary amine, sorry, and along with that KCl and H2 as a byproduct. Fine. So let's proceed with the next one. Identify the compound X and Y in the following conversion. Okay, fine. So first step is a very common to you and well known to you. So you are having the aniline. So in case you are having aniline and NaNO2 and HCl is given, so they will in situ, in this process in situ generation of HNO2 will take place, and that will diazotize the system, right? And you will get benzene diazonium chloride, N2Cl, right? And here, so that is my X, that is my X. Now if you want to get I further, so you just put some Ki and just vomit a little, okay? And you will end up with this iodobenzene, right, along with that KCl and N2. I guess you understood this as well. Please be careful, this question is going to be highly alert zone for the board. Let's proceed for the next one. Okay, so here you can see explain carbylamine reaction with equation that we already did in the last slide. Okay, this is the carbylamine reaction where primary amines, they actually reacts in this process, or aromatic primary amines also can proceed, where you have to give some chloroform and ethanolic potassium hydroxide, that will give you isocyanide as a product of foul smell, right? So there's the same answer over here. Let's proceed with the next one. Complete the following reaction. Okay, so you are having one benzene diazonium chloride. Here I have to provide HbF4. So once you are giving HbF4 and NaNO2, here you will end up with, here you can see this is the first question, allophatic and aromatic primary amines, the same thing I already explained here. And here comes the last part of the question. Here it's a IUPAC name of the particular thing. It's 1, 2, 3, 3 carbon system. From here you have to start numbering 1, 2, 3 like that. So it's propanamine. Okay. Let's proceed further. So this is one of the most important question. So I am writing it as a board alert. Okay, so here the first question is, how do you distinguish between primary, secondary and tertiary amines using the Heisenberg's reagent? And you have to write the chemical equation that is involving in this particular reaction. So Heisenberg reagent is basically, you can get a very small answer type question out of this particular thing as well, where they are asking only what is a Heisenberg reagent. Okay, so that is a benzene sulfonyl chloride. I always insist, write the formula of this particular thing, it will be helpful. So basically what happens whenever you are having a primary amine, you can see RNH2. Okay, after reacting with the benzene sulfonyl chloride, it will form something like this. This particular thing, so this portion you can avoid. Okay, after reacting with NaOH and HCl, this particular portion you can avoid. Okay, but this statement you have to mention that whatever the adduct it will form, that is soluble in aqueous NaOH. Soluble in aqueous NaOH. Next particular thing, it is a secondary amine, and again benzene diazonium chloride. You can see another hydrogen. This hydrogen will be replaced by this hydrogen, and this Cl actually they react. Okay, they react and they gets eliminated in the form of HCl, and that nitrogen and sulfur direct bond. Right? So this particular thing is insoluble in NaOH. Okay. Now look at the third one, the tertiary one. Here you can see there are no hydrogen at all. In this case, it is a tertiary one. There is no hydrogen. So here, this type of salt of benzene sulfonic acid is formed. This is insoluble in NaOH but soluble in HCl. Right? Soluble in HCl, because whenever it further reacts with HCl, it forms amine hydrochloride salt. You can see it's a charged system, and definitely it should be soluble in HCl. Okay, so this is the thing. So simple thing, first you mention what is the reagent with the chemical formula benzene sulfonyl chloride. After that, show one by one reaction. First with the primary one, then secondary one, the tertiary one. Primary one, you mention that it is soluble in aqueous NaOH. Okay, secondary one, you mention that it is insoluble in aqueous NaOH. Fine. And the tertiary one, whenever you are writing, just mention that it is insoluble in NaOH but it is soluble in HCl. Okay, so this is what they asked. Let's proceed. Okay, so here comes a 5 marks question. You can see, how would you prepare primary amine by Gabriel Thalamide synthesis? Given equation for this thing, what are the advantages, and give a reason why aromatic primary amines cannot be prepared by Gabriel Thalamide synthesis. Okay, so very important question. I am just writing it as a board alert. Okay, so let me show you how you should proceed with this reaction. So first you have to start with the thalamide, right? C double bond O, here also C double bond O, then connect them with NaH. So from here you have to start. What you have to give then? You have to give some KOH, right? Put some KOH, then what will happen? This thing will react. Okay, this is an acid, this is an base. Acid base reaction will take place, right? So once acid base reaction will take place, what it forms? It forms salt. So this is the salt that will be formed. Now what will happen? Here will be one nucleophilic attack. Now I am using any kind of alkyl halide type of thing, any kind of alkyl halide. Okay, so now here you can see N minus will act as a nucleophile, right? So N minus will act on R, it will attack on R, and X will leave as a leaving group. right? As a result of this, you will get a system something like this. So first step, you can see it's an acid-base reaction, salt formation, after that nucleophilic attack, right? So once the nucleophile is attacked, you will get the system something like this. Here you will get R. Now what do you have to do? Now you give NaOH in aqueous media, then this will be opened up and you will end up with this salt plus primary amine. Okay, so this is how you can get pure primary amine out of this reaction. So this is your Gabriel phthalimide reaction. Now what are the advantages? You can see here in this method 2 degree and 3 degree amines are not formed, right? So you will get pure primary amine, right? So 2 degree and 3 degree amine, there will be no chance of contamination. And another thing you can see, the last part give the reason, that is why aromatic primary amines cannot be prepared. So the reason is here. Just look at the alkyl halide group. Just a minute. Look at the alkyl halide group. For this case, if it is an aromatic compound, okay, aromatic halide, okay, there this nucleophile attack won't be possible, right? So why the reaction is taking place? Because this particular nucleophilic attack is possible, that's why the reaction is proceeding further. If this nucleophilic attack is not possible, if you are using one aromatic system along with the particular halogen, from where the nucleophile will attack, you tell me? There is no chance to attack. That's the reason it will not attack on the aromatic halide. Okay, as a result of this, you will not get aromatic amines out of it. Okay, I guess you understood this. Let's proceed further. Okay, explain Hoffman bromamide degradation reaction by taking butanamide as an example. Give the IUPAC name of the product. Okay, let's proceed further with the next chapter, that is the biomolecules. Okay, so here comes the number distribution of this chapter. You can see very small answer type question you can get maximum 2, small answer type question you can get maximum 1, large answer type you can get 1. Okay, let's proceed for the 1 marker question, that is the MCQ. So the number of amino acid in tetrapeptide. Okay, so like needless to say that as it is a tetrapeptide, so peptides are nothing but the linkage of the amino acid. So definitely tetra means 4. So C is going to be the correct option, right? Let's proceed further. Here you can see the alpha and beta forms of glucose. Okay, so what are they? You have different options. So just don't even think for this type of questions. So directly you can imagine alpha and beta is just because of they are anomers. Okay, you can see option C is there, anomers of glucose. This first carbon 1 you can see, this carbon 1 you can see, they are called as anomeric carbon. Okay, let's proceed. You can see which of the following statement is incorrect. Okay, proteins have polyamide chain while nucleic acid contain a polynucleotide chain. It's a true. Nucleic acids are long chain polymers of nucleotide. Absolutely true. Next one, RNA is major source of genetic information. Okay, so there comes the mistake. You can see as you already studied that DNA is the major source of genetic information, right? So this particular statement is going to be the incorrect one. Okay, I'm not going for the further one. I guess you got the answer. Let's proceed. What are the reducing sugar? Give an example. So reducing sugar means this sugar has an open aldehydic or ketone unit, okay, and those aldehydic units are eligible to reduce the Fellings and Tollens reagent. So that's the reason they are called as reducing sugar. You can see the carbohydrates which reduces the Fellings solution and Tollens reagents are called reducing sugar. Simple. Okay, and you can see the options are given: glucose, galactose, fructose. There are several options. They have one free aldehydic unit that actually performs the reduction. Okay, let's proceed. Give two methods for the preparation of glucose. So there are different methods you can see, and two of them we are just discussing here, like from sucrose, that is a cane sugar. So you can see sucrose is boiled with dilute HCl and H2SO4 in alcoholic media. Okay, so if sucrose is boiled here, you will get the mixture of glucose and fructose. So by default the glucose is formed in the media, right? Another thing is from starch. Okay, how you can get it is actually the commercial process. So you have to boil the starch with dilute H2SO4, right? And like some little bit of pressure also you need, and you will get that glucose as a product. Okay, this is a commercial process to prepare the glucose. I guess there is nothing like to be like more very conceptual or difficult. It is something to be by-hearted, or you can just recall the things. So you know, in biomolecules chapter, things comes from a specific zone. Okay, it's not like random questions are coming from here and there, and so much of concept, so much of difficulty, so much of complicacy are involved in the question. No, it's not like that. Rather, simple, a zone specific question comes. Like most of the time they are asking alternative here, either they ask reducing sugar or they are asking non-reducing sugar, this type of question. Okay, anomers related one question, what do you mean by anomers, what do you mean by epimers, this type of simple zone specific question they will ask. Okay, preparation of glucose related question. Okay, and structural approval, like how you should prove the structure of the glucose, how you should prove there are 6 carbon. Okay, these type of questions, general common questions used to come. Okay, don't make it complicated. Sometimes I heard students are saying that biomolecules chapters are very difficult because some difficult structures, glycosidic bond, etc., so many things are there. But really you don't have to be that much complicated while studying. Be specific, just find out what actually you need to study and proceed with it. Okay, now let's proceed with the next question. You can see, how does glucose react with hydrogen iodide, or how do you show that glucose contains 6 carbon atoms in a straight chain? This is the same question I just told you right now. So they will just ask you structure, how did you prove, right? Like glucose looks like this, how you can prove it? How do you know that? You can't see a glucose molecule, how you should prove the structure like this? So you have a number of tests that needs to be done that gives you, okay, the glucose comes like that. Okay, one of the tests is that is a hydrogen iodide. Okay, so if you do the hydrogen iodide test, you will get a straight chain. Okay, you will get the straight chain like in hexane. Okay, so that will tell you that okay, glucose contains a 6 carbon system. Okay, another thing you can see, how does glucose react with hydroxylamine, or how do you show that glucose contain one carbonyl group? So you can see the open carbonyl unit that is at the top here. Okay, so this is the first thing that you can see, HI and red P if you give, red phosphorus if you give, it will form this in hexane like system. So the cyclization will be opened up. Okay. Now here you can see once hydroxylamine you will give, it will form glucose oxime or glucose oxime, whatever you want to say, that will prove you, okay, glucose is having one open carbonyl unit or one aldehydic free unit. Okay, so this is how you can recall. Let's proceed further. Okay, so this is also a direct question. They always ask Howard's projection of any two structure. you can see first they are asking the alpha D glucose and beta D glucopyranose. Okay, so I guess the alpha D glucopyranose you know already, and this is the beta D glucopyranose. I already have it's given there. You just need to practice a little bit about the structure and you can do it. Let's proceed. Here you can see, write the Howard structure of the sucrose. Give reason sucrose is a non-reducing sugar. Mention the glycosidic linkage in sucrose or cane sugar. What is the invert sugar and what is the glycosidic bond? Okay, so here comes the answer. You can see the first one, I guess you know, 2 glucose unit, 1 glucose, 1 fructose. I need alpha D glucose and beta D fructose. If they condensed, means 1 unit of water must be released and 1 glycosidic unit. See here in the anomeric carbon, this is 1, in the carbon 1 I am having 1 OH, right, and here also I am having 1 OH in this carbon. So from there 1 unit of water will be released and here 1 glycosidic linkage will be formed, right. So as a result of this I will get sucrose. This is a sucrose structure. Okay, it's a disaccharide type of thing. Disaccharide, why? Because 2 unit of carbs, 2 unit of carbohydrates are attached in a glycosidic linkage, right. Okay, next part you can see, give reason sucrose is a non-reducing sugar. Okay, reducing groups of glucose and fructose are involved in glycosidic bond formation. Sucrose is non-reducing sugar. Okay, so whenever it is a reducing one, it forms the glycosidic linkage. But in case of sucrose, there is no further possibility to further make another glycosidic linkage with another sucrose, right. It proves that it's a non-reducing one. Okay, let's proceed. Mention the glycosidic linkage in sucrose or cane sugar. So as I told you, C1 here and C2 here, right. C1 for the alpha D glucose and C2 for the beta D fructose. They form the glycosidic linkage by eliminating 1 unit of water. Next part you can see, what is the invert sugar? Okay, so sucrose is basically dextrorotatory. Okay, I guess levorotatory and dextrorotatory, this concept a little bit you are having. So like if you are having like optically active molecule, if you are putting that particular sample of that molecule in the polarimeter, then the plane of polarized light gets rotated, right. It can rotate in the clockwise direction, it can rotate in the anti-clockwise direction as well. So if it rotates the plane of polarized light in the clockwise direction, it called as levorotatory. If in the anti-clockwise direction, you can call it dextrorotatory. Okay, sucrose, it's found to be dextrorotatory, but after hydrolysis it gives dextrorotatory glucose and levorotatory fructose. Okay, means overall sucrose gives you the dextrorotatory, but whenever it comes individually, whenever, see, if you break the glycosidic linkage, again you will get back your alpha D glucose and beta D fructose, right. If you individually again do the test, put them into the polarimeter, then you will get dextrorotatory glucose. This glucose will be dextrorotatory, means this glucose will rotate the plane of polarized light in anti-clockwise direction, but the fructose will rotate it in clockwise direction. So levorotatory fructose, right. But levorotation is more than that of the dextrorotation. Okay, so the mixture becomes levorotatory. Okay, because fructose comes more, means the optical rotation value itself it comes more, so it predominates. So overall it makes the overall solution levorotatory. So now you can see thus hydrolysis of sucrose brings about a change in the sign in rotation from dextro to levo. So that is called invert sugar. Okay, so for you people, again in a short I am telling it, overall sucrose dextrorotatory, fine. If you bake sucrose, you will get glucose and fructose, right. So glucose whatever you will get, it is dextro, and fructose whatever you will get, it is levo, right? Individually you will get, but the optical rotation value for the levorotatory fructose is more, that's why the value predominates. So overall solution it is a mixture of glucose and fructose, right? So that will give you the levorotatory value, levorotation, right? So as a result of this, initially you had, whenever you didn't do the hydrolysis, initially you had the dextrorotation, but after hydrolysis, when they are getting separated, then you are getting levorotation because of the majority of the fructose, not majority, rather than the more rotation value for the fructose. So initially it was dextro, now it is levo, that's why you can call it invert sugar. I guess you understood this. Let's proceed further. What is the glycosidic bond? You can see whenever two monosaccharide unit, I already explained it here, when two monosaccharide units are joined together by an oxide linkage, okay, by the loss of 1 unit of water, such a linkage between two monosaccharide unit through an oxygen atom, it's called the glycosidic linkage, okay. Here you can see in between glucose and fructose we are having the glycosidic linkage, okay. I guess you understood this. Let's proceed further. Okay, so we are going to proceed with our ultimate chapter, that is the chemical kinetics, okay. So the first question comes here. In the Arrhenius equation, the factor e power minus EA, this should be EA, minus EA by RT corresponds to the first collision frequency, proper orientation, the fraction of molecules with kinetic energy greater than EA, and threshold energy. Okay, so this particular question comes from the binary collision theory. So binary collision theory finally gives the Arrhenius equation that is very much well known. I guess you know, K equals to A into e power minus EA by RT, that particular thing, right? So this e power minus EA by RT actually represent those molecules which are having the energy more than that of the activation energy, means the fraction of molecule with kinetic energy more than that of the activation energy. Okay, so option C is going to be the correct one for this. Okay, means these many number of molecule, whoever is having the kinetic energy more than EA, they will further proceed for the product formation. Okay, so let's proceed. Okay, the unit of rate constant for a zero order reaction. So zero order reaction rate constant unit is quite similar to the unit of the rate itself. Okay, so overall in general, if you want to find out the unit of any rate constant, there is a trick actually. This is mole per liter 1 minus n second inverse. Okay, where n is the 0 here, where n is 0 here. So put the value here, everything the value you can put. So here if I put 0, because it's a zero order reaction, I will get mole liter inverse second inverse. So this is the answer. So this is going to be the mole liter inverse second inverse. So this is the inverse one. Okay, so option A is going to be the correct one. Let's proceed further. Inversion of cane sugar is an example of, it's a first order reaction. Okay, so better to say it's a pseudo first order type of reaction. Okay, let's proceed. What are the two criteria for the effective collision between the molecule in a chemical reaction? This is also part of the binary collision theory. Okay, so there comes different factor. So mainly 3 factor we actually focus. First is the orientation. Okay, so whenever, let's say, 2 type of molecule, two molecule, they are reacting. The reacting means I am having in a container, I am having A and I am having B as well. Okay, to give me a proper product, to end with a proper product, the molecule must collide. Okay, the molecule must collide. Okay, without the collision, further reaction will not be possible. And not only the collision must be from the proper direction. Let me give you an example. Let's take an example of SN2 reaction. SN2 reaction, we heard that the backside attack must be there. The nucleophile attack should be from the backside. If the nucleophile attack from the front side, it will not give you the effective product. Right? So first, one factor is effective collision. One factor you can write. One factor you can write the effective collision. And the second factor you should write the proper orientation. Okay, so the collision must be effective and the orientation means from the proper direction, right? And let's say, okay, two factors are done, the major factors. Another thing, let's say collision is also going on, it's in a proper orientation as well, but still there are chances that the reaction may not proceed. Why? Because the reaction mixture, that particular reactants must have some sort of energy. Okay, they must cross an energy barrier to give you the product. That particular energy barrier is called activation energy. So the last point I must write, that is the energy barrier. If all the effective collision will give you the product, then let me tell you, in 1 cc volume, in 1 second, there are possibilities to have 10 power 27 times collision. So just they are colliding and just you are just giving two reaction and they are just giving the product. It's not as simple as that. It's basically time consuming and it will give you the product in certain way. They will collide. The orientation must be proper, from proper direction. Another thing is they must cross this energy barrier, the activation energy barrier. Once the molecule, they are having proper activation energy, they can only proceed for the product formation. So these are the three factors. Let's proceed. Derive the integrated rate equation for the rate constant of the first order reaction. Okay, so let's proceed. It's a very easy one actually. Let me just start with a normal random reaction. Let's say A gives product. Okay, so for in general, if you want to write the rate of the reaction, so rate of the reaction I must write minus d of A divided by dt. Let's say this is my equation number 1. Another way, from the rate law I can write rate equals to rate constant into concentration of A power 1, because it's a first order reaction. It is 2. So both of them are equal to rate. So now I can equate them. So equating 1 and 2. So what I am going to do? Minus dA by dt equals to K into A. Now you have to proceed with the integration. So how? First, let's take the same term together. So minus dA by A equals to KT. Okay, now let's integrate. So you must write the line that integrating both sides. So while integrating, I must put some limit. Here I am multiplying this thing with dt, K of dt. Right? So now from here, whenever T equals to 0 means the reaction has not started. Okay, let me just modify this thing a little bit. So while you are just doing the integration, this T should be from then dt. Okay, when T equals to 0 means the reaction yet not started. So I am having the full reactant. So that full reactant is called as A0. When T equals to 0, amount of reactant is A0. When time equals to T equals to T, any random time, 1 minute, 2 minutes, 3 minutes means reaction a little bit ahead. Here let's say it is AT, right? So now let's proceed further here. From here, integration of dA by A, I will get ln of A, right? ln of A. So for this case, I will put the limit later. And here I will get simple KT, right? Here one minus sign was there. Okay, minus K. Let's put the limit over here from T to here 0. Okay, now as you know it is upper limit minus lower limit. So I can write ln of AT minus ln of A0, right, equals to minus K of T minus, let's directly put 0. Okay, so from here I am getting ln of AT by ln of A0 equals to minus KT, right? Because you know ln of A minus ln of B, it is ln A by B, right? So from here, just in order to do the sign modification, sign change, I am just taking the numerator to denominator. So ln A0 by AT, same thing, equals to KT. Fine. Now doing the solving the problems with ln is a little bit hectic because you know the exponential terms and all comes. So let's take it into the log. So how to convert ln to log? You have to multiply with 2.303. So 2.303 log A0 by AT is equals to KT. So from here K equals to rate constant equals to 2.303 by T into log A0 by AT. So this is the integrated form of first order, okay, integrated rate law. Fine. So everything is fine, but whenever after deriving the entire thing, it's a direct question comes actually, alternative year, zero order or first order reaction they ask to derive. So after deriving, please don't forget to mention what is A0, what is AT, what is T, what is K. Okay, so K is the rate constant here, T is the time, and A0 is the concentration of the reactant at T equals to 0, or initial concentration of the reactant also you can write, and AT is the reactant concentration at time T. Okay, so this is the entire thing. So pause your screen and make a note of it. I guess you are done. Let's proceed for the next one. Draw a graph of potential energy versus reaction coordinates showing the effect of catalyst. Okay, so let it be my potential energy and this is my reaction coordinates. In general what basically happens, you can just make the reactant a little bit energetically high and product a little bit energetically low, because in general what happens, like reactant, if it is energetically high means it's unstable, it has more urge to proceed for the products, right? So It's like that. Now whenever it is getting changed from reactant to product, the journey is not simple. The reactant to product like that it can't go. It actually proceeds through this particular pathway. Okay, so it has to cross a hill station like that. Okay, and the tip of the hill station here, this is called the transition state. Okay, this barrier that it covers, you can see this energy gap that it needs to cover to reach the tip of the hill station, and then you can come back to the destination, right? This particular energy gap is called activation energy. It's called activation energy. Okay, so now just imagine if I minimize this activation energy, or better to say if we can make a tunnel in between the hill station, then our journey will be even more easier. So catalyst actually creates that tunnel. So whenever you are using the catalyst, the journey becomes like that, right? Initially the activation energy was this much. Now look at the activation energy, it becomes this much. It becomes less. So whenever you are using catalyst, then activation energy gets decreased. As a result of this, the reactant gets converted to product faster, right? The similar way, you are just simply climbing a hill, or I am going through a tunnel. Which one is easier? Definitely I am going through a tunnel. It will be faster, it will be easier. So for this reaction, catalyst is the tunnel. Okay, it minimizes the activation energy, it minimizes the energy barrier, and thus the product formation becomes faster. I guess you understood this. Let's proceed further. Okay, mention any two factors which influences the rate of the reaction. There are so many factors. First factor, one of the important one that I can tell, is the concentration. In general, it may appear like if you increase the concentration of the reactant, there will be more collision and you can expect more number of product. But again, let me tell you, it's an experimental parameter. Sometimes it may happen that you are increasing the concentration of some particular reactant, but the reaction rate is not increasing at all. Okay, but in general, you can, if you just in general, it is observed that if you increase the concentration, the reaction rate usually it increases. Okay, another one important parameter, that is the temperature. So temperature, it is related in accordance to the Arrhenius equation. Definitely if you increase the temperature, the kinetic energy of the molecule increases. As a result of this, what happens? The more number of collision will take place, or effective collision will increase, and hence faster product formation you can observe. Or another point just for your information, usage of catalyst. As I told you in the last slide, if you use the catalyst, it will decrease the activation energy barrier, and hence you can expect more product formation. Okay, I guess you understood this. Let's proceed further. Okay, so this type of numerical problem you can expect from this chapter. More numerical problem we will be discussing. There will be a differentiation based on the numerical based problem. So I am really willing to look forward to that session where I can tell you different type of tips and tricks to solve numerical problems. So as of now, let's proceed with this. First order reaction is found to have a rate constant value this. find the half-life of the reaction. So half-life formula actually we have T half for the first order reaction is 0.693 divided by K, right? So this is a formula that we are very much familiar with. Now simply put the value over there. T half is going to be 0.693 divided by 5.5 into 10 power minus 14. If you just take the second up, so it will be second, right? Now if you just simply calculate it, you will end up with the answer almost, I guess, equals to 1.26 into 10 cube second. Okay, so these type of things you can expect over there. Please be assured that you are mentioning the unit, otherwise 1 marks will be deducted. Okay, let's proceed. Okay, so here comes the end, and I'm expecting that you people enjoyed this, you understood the concept, as well as it is a little bit or too much of help for your upcoming FA2 examination. Please keep solving more doubts, keep commenting what type of problem or what type of videos you actually need, and please don't forget to subscribe our channel. Thank you, and please wait for the next session. Some more interesting videos are coming. Thank you so much.